now we've gone through this analysis and we have our set of equations, but it turns out actually it is a little bit, I don't know, not tricky, but it's kind of annoying to solve the set of equations with this all the time. Really what you want to do is express the performance of a heat exchanger in terms of non-dimensional parameters that are pretty universal. So like things that you can really readily understand. It's a little hard to look at this and say, oh, my UA is a certain number. You know, this gives me this performance in a heat exchanger. Instead, you want to have something that's a little bit more tangible, a little bit simpler, something that you can put in tables and nice equations. So there's two ways that are normally done for that. One is the log mean temperature difference. That one has, I think, some problems. In fact, it's the equation itself for LMTD is undefined, right, at a perfectly balanced heat exchanger. So it's not really what you want. The better way to do it, the way the textbook does it, the way we'll do it in this class, is something called effectiveness-NTU. And so effectiveness is a measure of how much heat you're transferring across your heat exchanger. NTU is a non-dimensionalization of the size of the heat exchanger. Remember, UA is a dimensional representation. NTU is kind of an equivalent non-dimensional representation that's just normalized by capacitance rate. So we'll go through and now here's kind of where we stand, right? We have these three equations, this one, this one, this one. We're going to now come up with expressions for the same equations, but in terms of things called effectiveness and NTU. Okay. All right, so you might have seen something like this before. Effectiveness is one half of this. So effectiveness is defined as the amount of heat that you're getting across the heat exchanger, the amount of heat you're transferring, divided by the maximum possible amount of heat transfer. We'll talk a little bit more about what that means, but that's one of the parameters. There's this NTU parameter as well. And so if you have a given, let's say you have a given flow arrangement. We have a counterflow. We just did our counterflow here. So let's say you have a counterflow. You can express effectiveness in terms of the NTU and something called capacitance ratio. So capacitance ratio here, capacitance ratio is going to be defined as C dot min divided by C dot max. So remember, you have two capacitance rates that you care about, C dot C and C dot H. What you just want to do is take the minimum of those two and divide it by the maximum of those two, and that gives you a capacitance ratio. Capacitance ratio for perfectly balanced would be, so if it's balanced, it would be equal to 1. That means the capacitance ratio, the rate on one side is equal to the other exactly. That's what we call a perfectly balanced heat exchanger. If you have a capacitance ratio of 0, that's saying that I could essentially add an infinite amount of heat to one fluid stream and not have it change temperature at all compared to the other. Right? So you take all the heat out of one fluid, it's not going to at all change the temperature of the other fluid. So it's what we call a really unbalanced heat exchanger. Okay, but anyway, so we have this table. You can go see these things. And what I want to do quickly here is actually walk through where do we get these expressions from the set of equations that we started with. Let's go through that. I think at this point, you probably are ready to do that. Kind of for this class, we didn't really do it before. So let's just go through and do that. But anyways, what you end up with here is a couple different options for expressing these different geometries in terms of effectiveness and NTU. Okay, so let's go through and see how we actually convert our equations into effectiveness NTU representation. All right, so first thing, let's define effectiveness. So effectiveness is, we give it the symbol epsilon. Effectiveness is, like I said, the actual heat transfer across fluid, Q dot, so that's from one fluid to the other, divided by Q dot max. And the maybe interesting question is, what is Q dot max? What's the maximum heat transfer you could have? Well, let's get to that in a second here. So first, let's write these things out. So we have our two flow streams. So Q dot is going to be, for the cold flow stream, C dot C times TC out minus TC in. That's the Q dot for one of the two flow streams. That was one of our two energy balance equations. The other was Q dot is equal to C dot H times TH in minus TH out. Right, so those should be equal to each other. All the heat's going from one fluid to another. So the question is, what is this maximum? So what would the maximum rate of heat transfer be if we were to look at, let's say start on the top. So on the cold stream, what would the maximum rate of heat transfer be for the cold stream that it could achieve? That would be, well, we know the fluid is moving with C dot C, right? That's not changing. We have a given M dot C and we have a given specific heat, we'll assume it's constant. But what would the temperatures be? The temperatures that would correspond to the maximum heat transfer rate on the cold side. That would be, if I went from, if my TC out went all the way to, if it went all the way to TH in, right? That would be the hottest that the cold outlet could possibly get. If my TC in remains constant, right, that's the coldest we could possibly get. That's the maximum rate of heat transfer you could get in the cold stream. So this is my max Q dot. Same thing for the hot side, but now we're limited by the hot capacitance rate. Mass flow and C for hot are not changing. So that's the case there, but then what would the temperatures be? Well, again, it'd be, I know I'm coming in with TH in. The coldest I could possibly get my hot flow would be TC in. And so this is, again, the maximum Q dot that we could achieve in either case. So the actual maximum for this device is going to be one of these two things, right? C dot C times that temperature difference, or C dot H times that temperature difference. And the maximum that could be possibly achieved would be the smaller of these two things. Right, so think about that, hopefully it makes sense. The smaller of those two is going to limit the rate of heat transfer. Okay, so we would say then Q dot max is equal to the minimum of Q dot max C and Q dot max H, right? Where these up here are the Q dot maxes. And so it's the smaller of those two things, which would just mean you're evaluating the minimum of C dot C times TH in minus T C in and C dot H TH in minus TC in. So the smaller of those things would be your maximum. We can also just write this for simplicity's sake as Q dot max is equal to C dot min times TH in minus TC. Okay, so my effectiveness then is just the following. It's just my actual Q dot that I get divided by C dot min TH in minus TC in. Okay, so we now have our definition of effectiveness. Just over here in the corner, maybe do our definition of NTU. It's pretty straightforward. So NTU is a normalized size of the heat exchanger. And so if we're talking about a normalized size of the heat exchanger, we know that right, that's going to be proportional to UA in some way. So the larger the actual physical area, the larger the heat transfer coefficient corresponding with that area, the larger the number of transfer units is going to be. But it has to be normalized in some way. So we could, for a given device, let's think about this kind of thought experiment. So for a given UA, what would happen if I took the C dot, the capacitance rate, and slowed it way down, right? Made it basically like creeping flow through that device. You would expect to see really good, really effective heat transfer in that device because it's basically way oversized for the flow that it's getting, right? So we actually take NTU and normalize it by C dot. And so this is going to be C dot min. Okay. So you can, once you have your relationship for effectiveness in NTU, you can use these definitions to go back to quantities, dimensional quantities that you actually care about. Okay, so let's take that step then of using these definitions, right? We'll use this effectiveness, we'll use this NTU, and let's plug them back into that equation that we derived before and get to the equations that we saw on the table. Okay, so let's, rewrote what we have here. So what we want to do is express our Q dots in terms of effectiveness. So to do that, let's maybe start with the TC out. So let's write our TC out equation, this one over here. We'll solve for that, and it becomes TC out is equal to TC in. So now let's use our definition of effectiveness and rewrite that equation with effectiveness in there. So that's going to be effectiveness times C dot min times TH in minus TC in divided by C dot C. So it's the same equation now, just written in terms of effectiveness. Let's see, we can do the same thing for TH. So TH becomes TH out is equal to TH in plus, sorry, it's going to be minus now, not plus, minus effectiveness times C dot min, TH in minus TC in divided by C dot H. Okay, so let's take these now. So this is going to go, so TC out is going to get substituted in here. TH out is going to get substituted in here. And then we end up with kind of a messy equation, but we'll see how it ends up simplifying out. Okay, so write this out. So it's going to be ln of all this stuff substituted in. So we're going to have TH in minus effectiveness. Now we have C dot min over C dot H. TH in minus TC in. Okay, so that's what we substituted in, then minus TC in on the numerator, then divide that all by the TC out substitution. So that becomes TH in minus TC in minus epsilon C dot min over C dot C times TH in minus TC in. Okay, and then that's equal to what's on the right-hand side, minus UA times 1 over C dot H minus 1 over C dot C. Okay, so kind of messy, but there's some stuff we can do here. We can group together the TH and THN and TCNs, cancel some of that stuff out, and we end up with just rewriting it a little bit here. We have ln of, so pull the TH and TC out, so that becomes THN minus TCN times 1 minus effectiveness C dot min over C dot H in the numerator, and the denominator is also THN minus TCN. And then we have 1 minus effectiveness C dot min over C dot C. Again, equal to minus UA 1 over C dot H minus 1 over C dot C. Okay. Good. So now we can cancel out our THs, right? Or TH minus TC. That's the same on both sides. So this goes away. This goes away. Okay, and then we end up with something that's getting much closer to what we actually would see in the table, right? The actual expression that we're using. So let's jog up here to the top. We end up with ln of, actually, rather than, let me just give you the definition here. So what we need to do is, you see down here we have this, we have C.H and we have C.C, we have C.min. We don't know which of C.H or C.C is going to be C.min. We don't know which of those two. So actually what we want to do now is just make an assumption. We can say, let's assume that, say, C.C is the minimum, and go through the analysis and solve the problem. It actually doesn't matter in the end. Either way, it's going to come out the same. But for now, it just helps us to make it more concrete, to just make an assumption. So what I did was, I made the assumption C.max is equal to C.h, and C.min is equal to C.c. So this is just some blind assumption. It doesn't really matter. It all comes out on the end. We plug that in. So what we're going to do is plug in, anytime you see C.h, we're going to call that C.max. Anytime you see C.c, we'll call that C.min. And you end up with the following. You end up with ln of 1 minus epsilon C.min over what? C.h, and we call that C.max. So C.max divided by 1 minus epsilon C.min divided by C.c. Well, that's C.min. So that's just 1, right? So it just is this. Right? And then on the right-hand side, we have minus UA. Let's see, minus UA. What I'm going to do is, so we have 1 over C.h. So C.h was C.max. Max minus 1 over C.min. Right? And actually, what I want to do is I want to normalize UA by C.min, so that I can call that NTU. So I'm going to multiply by C.min over C.min. C.min here, and then the ones up here become C.min and C.min. Okay, a little messy. But maybe you can see what's happening here, right? So now we have, you can see what's happening if I write it clearly. So C.min over C.max and C.min over C.min. So on the right-hand side, we actually simplify this out quite a bit. This all then becomes this nice compact expression, which is ln of 1 minus epsilon. This thing here is my capacitance ratio, right? So it's actually 1 minus epsilon times capacitance ratio, CR, over 1 minus epsilon is equal to UA over C.min is going to be NTU. So it's minus NTU times, again, C.min over C.max is capacitance ratio minus 1. Right? So we went through that kind of tedious analysis, but now if we compare this expression back up here to the table, yeah, we should see that that's the expression. So this is going to be solved now for effectiveness or solved for NTU. You'll see it on either side. Okay. Actually, I have this down here with some notes. So that's the solution. Questions on that? So yeah, the question then for me is, okay, we have these two different representations. We have one in terms of effectiveness, one in terms of NTU. Obviously, you may come into a situation where you want one or the other just because of the equations that you have. But there's maybe a subtler point to this. There's two situations in which you're going to want to use these. One is you're designing a heat exchanger, and you want to specify something about how much heat is transferred in this device. The other is maybe you have an existing heat exchanger. It's already got a size to it, and you just want to characterize that existing heat exchanger. So the first type, we'll call that design type. So this over here would be design. So if you're designing a heat exchanger, you're going to want to know, how big do I make this thing? What's my NTU? So let's say I know I want to transfer 70% of the heat, right? Effectiveness is 70%. Plug in your effectiveness there, your desired effectiveness, and then you get back your non-dimensional size, and then you can get the UA from that. So that would be a design type problem. Over here, this would be kind of a simulation. simulation type problem where you have an existing heat exchanger, it has an NTU, you're just trying to figure out how effective is my heat exchanger.